Hello everybody, this video is going to be a quick review of kinetics. By the end of this lesson, you should remember some of the things we learned from Honors Chem about the different ways we can measure reaction rates. So just a reminder that kinetics is the study of reaction rates and also the mechanisms, how they happen. When we talk about reaction rate, we're talking about the speed of a particular chemical reaction. You could either measure how fast the products are being made, or you could measure how fast the reactants are used up. Sometimes it's easier to measure the formation of products. Sometimes it's easier to measure how fast the reactants are disappearing. And the reason we care about kinetics is that sometimes it's important to be able to speed up a reaction to encourage it to go faster. Sometimes we want to slow it down so it doesn't get out of control. Sometimes we're interested in the mechanism. We want to learn how it's physically happening step by step, and the speed of the reaction can give us some clues as to how those mechanisms are occurring. So we define rate as the quantity of something changing over a given period of time. And this is something we see every single day. For example, when you drive in a car, the speed of the car is a rate, the distance it has traveled over a given period of time. So when you're driving in your car, the speed, the rate of our car is typically measured in miles per hour. Now, in a chemical reaction, we're not obviously going to use miles, right? And often reactions are pretty fast, so we don't usually use hours. It's more common to see seconds. So if I wanted to write the rate of a reaction, it would look something like this. This would be describing how quickly iodine was disappearing over a specific amount of time. We measure in concentrations. That's why you see the square brackets. If we are measuring how fast a product is being made, the rate is going to end up with a positive value. If we're measuring how fast something's being used up, it would have a negative value. If you think about literally doing the subtraction, right, if you end with less than you started with, final minus initial ends up giving you a negative sign. Now, we often want to be able to compare our reactants and products to each other. So to help with that comparison, we stick an extra negative sign in front of any of the reactants. That way, when we have a negative of a negative, we typically are able to express our rate as a positive when comparing it to other things. Sometimes people get a little tripped up on the double negatives on things. Yes, a reactant has a negative change, but if we're talking about the rate of the overall reaction, we tend to express that as a positive by throwing this double negative in there. We can see it on a graph like this. You could measure the disappearance of your reactants, seeing how fast this green line is decreasing. Or you could measure how fast your products are appearing, the blue line and the red line. The slope of the line helps you figure out if it was a reactant or a product. You should notice that the blue line and the red line don't have the same slope, do they? One of them is increasing twice as fast as the other one, because these rates are proportional to the stoichiometry, to the coefficients that we see in the balanced reaction. When you look here, you can see that nitrogen monoxide is being made at twice the rate as the oxygen. And you can see that here, its slope is twice what the oxygen is. We can measure at a specific time what the slope is by taking a tangent line. If you remember from math class, If I want to know the slope at an exact point on that line, we need a tangent. Remember, a tangent line is one where you have an equal gap on this side and this side. When we're doing it by hand, use a ruler, do your best. If you have access to Excel or a graphing calculator, you can make it calculate that for you. One thing that's important is to notice that the rate is not constant. As we start to lose reactants, it starts to slow down. When we first start, there's a much steeper rate of production of our products, and then it slows down. So it's not a constant speed, which is challenging because then you have to decide, well, what time do I measure the rate? Am I taking an average over the entire thing? It's not a constant value. So here's just another example where we have a graph. If you look at this, you should be able to figure out pretty fast that the red line are your products and the green line were the reactants. We have a positive rate for the products and a negative rate for the reactants. The red line is a positive slope, the green line is a negative slope. Now, usually, most of our balanced equations do not have coefficients that match for every piece. Here you can see a 1, and a 2. Because they don't get made and used at exactly the same rate due to the coefficients, we have to take that into account when we start to do our math. So we can see here in this example, every time we use up 1 mole of H2, we are also using up 1 mole of I2. But we would be producing 2 moles of HI. This would have a much steeper slope. Those coefficients, that stoichiometry, affects the rate of change for these components, which makes it difficult to relate things to each other. We don't like relating apples and oranges. We always want to be relating apples and apples. We see that constantly throughout the year. We want things to be consistent. We want to make sure that what we're comparing is apples to apples. So to account for the stoichiometry so that we can relate the rate of reaction to any of the chemicals present, what we're going to do is multiply each rate by 1 over its coefficient from the balanced reaction. So you can see here, whatever the coefficient was for chemical A ends up on the bottom. The coefficient for chemical B, chemical C, and chemical D. In this example, A and B are reactants. I can tell because I put a negative sign here. And I can tell that these ones are products because they're positive. Because delta A over delta T is a negative number, a negative of a negative is positive, which allows me to set it equal to the products because those are positive values. So the rate of reaction can be expressed by using numbers from A, from B, from C, or from D, whichever one is more convenient to measure. By dividing by these coefficients, we're able to equalize everything and make it so that we're comparing apples to apples. Another way we can take a rate is an average rate. An average rate is where we take the overall change in concentration over an entire period of time. That's a pretty big approximation because that curve does not have a constant slope. The longer your time interval, the more exaggerated your averaging becomes, right? You're deviating more and more from the true rate at an instantaneous point. But sometimes an average rate is good enough. Sometimes an average rate is all we're able to easily get. Just depends on what we're doing, why you might want average rate versus instantaneous rate. The instantaneous rate is that one where we're taking the tangent at a particular point. Now, those of you who love calculus, maybe you're thinking, oh yay, maybe we get to do some of that derivative stuff. No, we don't do calculus here. We don't have that math prereq for this course. In college, they do have calculus as part of the requirement for chemistry majors, because you do get to the point where you start doing the actual calculus behind some of this. But for our purposes, we'll never get to that point. So if I want to use this equation, we can see it represented here on the graph. If I want to find the instantaneous rate at 50 seconds, what I need to do is I come over here and I find 50 seconds. There's my little tangent point, right? And I'm going to take the change in concentration over the change in time for that tangent line. And that gives me the rate at that moment. But maybe I want to relate this to the HI being produced, not how quickly the hydrogen is going away. So what I have to do is I have to do the same type of calculation, but I'm going to have to divide by 2 because I want to know the rate for the whole reaction in terms of this, but I don't want to deal with the fact that this has been doubled. Oh, and you should notice here, right, we had a double negative that canceled out. So the rate of the reaction is 0.0070 molarity per second. So if I draw my tangent line at 50 seconds for the product, I'm going to have the change in concentration over the change in time divided by my coefficient. And what do you notice? You get the exact same answer, don't you? It doesn't matter if I'm measuring the disappearance of a reactant or the appearance of a product. It doesn't matter what my coefficients are. All of that gets kind of balanced out by taking into account the coefficients here and the double negatives for my reactants. So we say that the rate of the reaction at 50 seconds is 0.0070, regardless of which chemical you're measuring. Different things can affect the reaction rate. We say the nature of the reactants plays a role. So what kind of reactants do you have? What kind of physical condition are they in? There's all sorts of generalities, like small molecules tend to react faster than big ones. Gases tend to react faster than liquids, which are faster than solids. Remember, whenever we make these kind of general statements, yes, obviously there are exceptions, but that is far beyond our capabilities of dealing with at this level. If you have a powdered solid, maybe imagine like granulated sugar versus a sugar cube, you have a lot more surface area, so the molecules can interact faster. Some types of chemicals are more reactive than others. Remember that reactivity series? We take into account things like ionization energies, what types of reactions they like to do. Ions tend to be faster than actual molecules because we don't have to deal with covalent bonds that needing to be broken. So those tend to be faster reactions. We can also take into account things like the temperature. Raising the temperature generally increases the reaction rate. We have something called the chemist's rule, which is not a very good rule, but it's good for approximating things, making best guesses. We like to say that every time you raise the temperature 10 degrees, the speed doubles. Doesn't always work, but it's a pretty good guess. There are complicated equations that you can use to figure out how the temperature change is specifically changing the reaction rate, not something we're dealing with right now in this lesson. Catalysts can also affect the reaction rate. A catalyst helps the reaction go faster, but they're not considered a reactant because they're not used up. When you start with a catalyst, it does something during the reaction, but then it's present at the end. We say it gets replenished. Sometimes you might hear that phrase. Most of the catalysts we think of are what are called positive catalysts that make things go faster. They're providing an alternate pathway that has a lower activation energy so that it can go a lot faster, quicker. Negative catalysts, we usually hear the term inhibitors. They're things that slow a reaction down. Sometimes that's good. Sometimes that's what we're after. Catalysts can come in two types. Also, we can have homogeneous, where they're in the same phase, or we can have heterogeneous, where they're in different phases. There's an entire branch of chemistry called catalysis. It gets really weird and complicated really fast. I think it's really fascinating stuff. I love some of the chemistry about solid phase catalysts. It's really interesting how they work, well beyond what we're doing here. If we understand the different types of catalysts, if we understand the general concept on how they work, if you can kind of identify what a catalyst is during a reaction by looking at the equations, that's all we need. And then lastly, concentration. The higher your concentration, the more often the molecules will collide with each other, which is going to lead to a higher frequency of the products being made. Gases can have their concentrations be basically correlated to their pressures. So the higher the pressure, the higher the concentration. It's kind of the equivalent. And then one thing to make sure that you are always paying attention to on these problems is looking at that molarity, because the molarity of a solution is telling you what the concentration is. And all of these things that we're talking about relate back to that collision theory that you learned about in Honors Chem. That particles need to collide, and they need to collide hard enough, and they need to collide with the correct orientation. So things like raising the temperature increases how hard they're hitting, increases how often they're hitting. When we increase the concentration, it's impacting how often they're hitting each other. Catalysts can sometimes help with the orientation of their collisions. All of these things come back to the fact that those molecules have to hit each other for a reaction to happen. So I hope that was a good little refresher on some of the intro to kinetics things that you learned in Honors Chem, and I hope that was helpful. Bye, everybody.